So good evening to you all. Welcome to a second in our series of webinars discussing heat pumps with Mike Teahan of RBSI. My name, if you don't know already, is Stephen McGovern of the Cork Energy Consultancy. I've been an assessor since 2008, working now primarily in the commercial and multi-unit residential sectors, amongst many other things. So I'll be deputising for our chair, Ollie Walsh, this evening. A little background, I joined the committee this year. And as many of you will be aware, one of the legacies of our previous committees and continued by the new committee was to establish working streams within the committee group. So with the idea of that was to improving the association and better representing the voice of our members through focusing committee members on different aspects of work within the group. I was assigned on to the training and event stream, along with John Barrett, Liam Donoghue and Michael Coyle, and our focus will be delivering on these type of training events online, and we hope in person, hopefully, when the COVID cloud finally lifts. This is a very important and timely project, we feel, as the importance of upscaling and retaining information will become more important, we feel, especially as the transition from the old QA process and the biannual exam regimes within SCAI to more progressive training continuous development process events such as this, we hope will play a major part in contributing to that. We initially hoped that when we formed this group that by the time that would be kind of a quick process and that it would get up and running quite quickly, but there's a lot of stuff going on behind the scenes, I guess, in SCAI in organising this and getting it up and running. So we don't yet have clarity on how this will be rolled out, but we thought it would be better to go ahead and get some contact with our members and get some content out there in these training events that we hope will be useful to our members. We will break from having webinars now for 2 months during the summer, but we hope to be back in September with a bang and with maybe lots more clarity on that whole position of CPD process and how it will roll out. We'd like to invite you all to become more involved in the association. If you're not already a member, please do join. And if you are a member, don't forget to renew and tell all your friends about it and other assessors who may not have joined, because I think it is really important that we group together as sole traders and we work solely, a lot of us. So I think it's important that we kind of form this association so that we can channel our feedback to SCAI in a consolidated way. So we'd love to hear from you in relation to any issues that you might have out there, generally working as an assessor. And in particular, if you have any feedback on the new advisory report format, we'd love to hear your thoughts on it. So you can contact us through our admin@berassessors.com email or chair@assessors.com email. We'd really love to hear from more feedback and how we think we can better represent you. And from the training point of view, I'd love to hear from you about any topics you'd like us to cover for training. Speakers, be they speakers or topics, or if you know of anybody or that would have insights that you think would be of interest to our members, please contact me, and that's training@berassessors.com is the email there, so feel free to contact us. So yeah, I think our attendees are looking solid at the moment, so I think we can move on. So we initially thought that this would be, as I was saying, so we think we attendees, so we would like to welcome back Mike Teahan this evening to continue and conclude this current series, which took us from exhaust air heat pumps and their entry into deep to the pitfalls of not correctly sizing them last week. We initially thought that this would be a 2 weeks would cover this topic, but after chatting with Mike after last week's webinar, we thought we'd covered more ground than we had hoped. So tonight we decided to let Mike maybe tie up any loose ends he wanted to cover on that topic, but also to move on more generally to group heat pumps and how they're entered in deep, and maybe interrogate that a little bit further. So of course, if you have any questions during tonight's webinar or on last week's webinar even, put them in the chat function there and we'll try to come to them later. So without further ado, we'll move on with a quick introduction to Mike again. So Mike is a highly qualified technical director at RBSI, specialising in the design of heating systems, and is highly regarded within the industry as an authority on renewable heating solutions. Mike is an expert in heat pump technology, offering solutions for residential developments, commercial applications and retrofits. Mike has been involved in the design, supply, install, commissioning of several thousand heat pump systems, including award-winning domestic and commercial systems with SAI. So we'll hand it over to you, Mike.
Okay, great. Thanks, Tim. Evening all. As Stephen said today, we kind of covered a lot of stuff last week on residential exhaust air heat pumps and the entry of same into your DEP. Also on the pitfalls of where you can get caught up pretty badly with exhaust air heat pumps because they're not so straightforward as your typical Hitachi Daikin split, as you would see. Like a 9 kilowatt split is a 9 kilowatt split. A 3 kilowatt exhaust air is not necessarily a 3 kilowatt exhaust air. And we went through the enthalpy calculation to show what is the true output of exhaust air heat pumps based on the input temperature, the leaving temperature, and the airflow volumes. So that was crucial from a design point of view, that you should look at, okay, is this heat pump big enough to heat my room or not? We covered that quite a lot, so I think we're going to do a little bit on group heating, cooling, ventilation, and hot water systems. We've been asked a lot lately to look at this as an option for residential apartment blocks because there's a lot of overheating happening in them. And we spent about 6 months looking at various options out there for combined heating, cooling, and ventilation solutions. And Swagon came up with a very nifty solution that I'm going to go through with you now. We've spent about 4 or 5 months going through this with the SAI for how we input this into DEP from a central system point of view, and we came back with fairly simple and straightforward methodologies, which I will explain as well. Anyway, so without further ado, I'll just share my screen here and we can go through this presentation. There's about 20 slides and about 4 or 5 short videos that explain things a bit better. You can't beat a video for explaining stuff. Again, throughout the presentation, if you have any questions, just, there's only a handful of us here tonight, so you can unmute yourself and ask a question, or just throw a question into the chat box and we'll come back. Okay. Okay, hopefully you can all see the screen now.
Yeah, we can see that, Mike.
Okay, great. Okay, today's topic, group scheme, heating with cooling as well, not just heating on its own, because heating on its own, it can be done quite easily with radiators or underflow heating. You can't do cooling really with radiators because you end up with a very wet apartment through condensation. So it'll be through an air-based heating system, heating and cooling and ventilation, air quality, and a little bit of hot water. And last bit, just to show the new workbook, how you input larger non-domestic heat pumps to get your seasonal performance factor out of it. So the solution here, it comes from Swagon. It's very much like a hotel solution where you have a thing called a chill beam or a supply air unit installed above your doorway, entryway, or in the ceiling or in your corridor facing into the room, supplying warm air or cold air depending on your need. You'll have a central air handling unit or an AHU on the roof. And you'll also have a central 4-pipe heat pump. Just ask everyone there if they could mute their mic and they come in. Here's some background noise. Okay, so the functionality of it is that you have your Paragon unit in the ceiling here above the doorway, like a typical hotel solution or apartment solution above the doorway here. And that's supplying your fresh air into the room via the central AHU. Okay, so as I said, A is your primary air supplied by the AHU into the top of the beam. This will be your Part F guidelines, 25, 30, 35 litres per second, whatever the size of the apartment or the room needs to have. That's supplied in by the AHU into the back of the beam under positive pressure. Fresh air then is recirculated around the room. So the B arrows there go across the ceiling, down the wall, and across the floor. So that's roughly 25% of your total air volume is fresh air, and around 75% of the air returned is through recirculation. So 25% here in your A side as fresh air, and around 75% of the air volume passing through the beam is recirculation air volume. So because you're creating a negative pressure inside the beam here through the positive pressure from the supply air, you create a negative upward trend of the air to flow into the beam. So that gives you natural induction. So you're getting, like I said, 25% fresh air, and you're getting roughly 75% recirc air through a negative pressure under the beam. And then lastly, your return air is going back into the ensuite or bathroom or kitchen and back to your central AHU. So an overview would look something like this. So there's your heat pump, chiller, 4-pipe heat pump. Now this is showing 2 pipes here, but in this case you'd have 4 pipes. So this is your chill water circuit or heating water circuit going to your AHU. You'll also have a heating, cooling water circuit coming down along here into the back of the beams. So heating circuit, cooling circuit, heating circuit, cooling circuit, heating circuit, cooling circuit, and so on. Your fresh air is coming in from the beam, from the AHU in here, up to the heat exchanger, out, down into the back of your chill beams, and your return air coming back up along here into your AHU. So a typical schematic would look like this for your VCD or your volume damper controls. So you'll have your AHU here on the roof, supplying your fresh air down into your variable control dampers into each apartment. These are factory preset to the right airflow depending on the Part F requirements. Okay. Okay, inside the chill beam is very like a fan coil, except there's no fan or there's no wet coil. It's a dry coil. So inside the fan coil, you'd have a fan blowing out the air. Inside the chill beam, there's no actual fan. The air pressure is coming from the central AHU. So with the compact changeover valve, this 4A valve here, this will decide whether there is heating water going to the chill beam or there's cooling water going to the chill beam. And this is done via the room sensor, via air quality control or room temperature sensor. So the reason why this works quite well is because in typical fan coils or typical chill beams, you'd have a heating coil and a cooling coil. In this case, you've one coil, and the 4-way valve will send either all the water through the coil for cooling or all through for heating. Typically, you'd see 2 coils, one coil for heating and one coil for cooling. So therefore, your surface area is halved. With the Swagon Paragon solution, you have one coil, so the surface area is much, much bigger. So you're getting much larger cooling capacity, much larger heating capacity out of the same one coil instead of having 2 separate coils. And this 4-way valve is a very clever solution. It's designed to send the chill water to the maximum surface area as possible. So you get faster air conditioning and faster cooling if the room was empty for a long period of time instead of waiting for twice as long with a smaller coil. Okay, from an output point of view, the Paragon wall or ceiling unit can give you up to 2.8 kilowatts of cooling. Now that's a very high volume of airflow, or 4.5 kilowatts of heating. Again, a very high volume of airflow. In your typical, 2-person bedroom, you might need about 800 watts of heating or cooling. So your capacity here is quite high. So at very low airflow rates, we'll say 10, 12 liters per second, you get about your 1 kilowatt of heating and 1 kilowatt of cooling from your chill beam. It also comes with supply air kits and return air kits for air volume dampening and for balancing the system. These systems here are pre-configured in the factory. So if you had 3 different bedrooms with 3 different air volume demands, the factory will preset those air dampers for you. And when you're commissioning the system, your handheld device will then allow you to preset or pick the damper per the room, and it'll automatically be set from the factory. Also, because there's no fan inside in these chill beams, the noise in the room is actually really, really low, because in a typical fan coil, you'd have a fan, and over time, that fan starts to rattle and vibrate because it gets dirty. With a chill beam, there is no fan inside it. The fan is way up on the roof or way back down the road. So the noise level at the actual chill beam is very, very low, 26 decibels, which is pretty much inaudible. Okay, just more overview picture of it. You'll see the supply air attenuator and damper coming in here from the AHU, supplying the correct amount of fresh air into the beam. You have your heating circuit, water circuit at maybe 45, 40, circulating around the building into your 2-port valves, your 4-way valve, straight changeover valve. and your chilled water. You notice here the chilled water is not your typical 6 and 12 as you would have with a normal chiller. If you had 6 and 12 here, you'd have condensation happening on the coil, and therefore you need to have a condensation tray to take away any condensation overflow. That's again a higher cost and less efficiency on your chiller. When you're using chill beams, you can actually go as high as 1421. Therefore, you're above dew point on the coil, which means you don't get any wet coils. Therefore, you don't need to have a condensation tray to take away any condensate. It also means your chiller is working at a very high efficiency because you're not trying to cool down the water to 6 degrees. You're cooling it down to 14, which means even for half the year, you can use some free cooling, using free cooling coils in the roof instead of an actual heat pump, using simple fans over a coil because the air temperature can be cooler than 14 degrees. Therefore, you can get a lot of free cooling using chill beams compared to a chiller, which needs to have 6 degrees. You have to have the air temperature below 6 degrees to get free cooling, which means you'd actually need heating more than cooling. So the free cooling side of it is very handy. Okay, so you have your heating at 4540, your cooling at 1421, and which means your chiller efficiency is very, very high. The range of products that you can get from the Swagon is your typical air diffuser. You have your Wise Parasol, which is your ceiling mounted office type solution, or hotel solution, or you can have your Wise Paragon, which is the one we were looking at mostly for this application. So you have this over your bulkhead, your return air is coming in the back, in the bottom here, and your fresh air is coming out. And again, like I said, it's mostly recirc here with about 25% fresh. Then you have your pre-configured dampers. These are pre-configured in the factory to whatever airflow we need per beam. These are also wireless. So this is wireless, your four-way valve is wireless, your room sensor is wireless, your air quality sensor is wireless, and they all talk together on a same Wise network. Okay, the other options for controls is that you have sensors that can have lots of sensing in it. You can have VOC, which is air quality, room temperature, and RH, room humidity. So you can have one sensor doing the lot, or you can also have motion sensors or human sensors, presence sensors, so on and so on, all linked to the same chill beam to give you the correct air quality and correct indoor climate based on RH, temperature, and VOC. So there's a snapshot of the actual wall units. You can have an RH and temperature sensor. You can have a simple set point temperature sensor. Or you can have the multi one, which is the all combined in one with VOC or CO2, or room temperature and RH. So you can have your air quality in your apartment really controlled to a pretty good degree based on both VOC and RH. It's becoming more and more important in buildings. We're living more and more at home as well. We're spending 80% of our time indoors. So air quality and relative humidity is becoming very important. And with this solution that we're looking at, it controls that room humidity and air quality very accurately, also along with room temperature, of course. Okay, other accessories, condensation sensors, if needs be. If you want to drop the temperature a bit cooler, you can bring condensation sensors or radio extenders if you're looking to go long distances. Okay, so how it works is that you have a unit called a detector, or director, which is controlling all these appliances here. So you have your chill beams, your sensors, your dampers, your extenders, and so on and so on. These are all wireless radio communication to this director. And one director, then is linked to, it's called a superwise. That's your main kind of hub for all your directors and your controls come back to one point. These are all wireless. This is wired back to the superwise. It then goes to your AHU and your BMS. So literally from the BMS, you can control your AHU and all your heating and cooling appliances remotely using the Wise system. And again, which is very handy, is all these control points here are wireless, which means if you have to change a room sensor or move a room sensor, or let's say it's an office application, you want to move around office walls, you can easily adapt the system because you don't have to be looking at cables to move appliances around. They're all wireless. Okay, so like I said, I have a few videos here as well, which kind of give you a more in-depth look at it. So there's 2 or 3 videos here in sequence. They're about between 2 and 5 minutes long. So we'll have a quick look at these, and any questions afterwards, we can talk some more.
As a hotel guest, you always have high expectations of the room. It has to be comfortable and clean, but also quiet, draft-free, and have the perfect temperature. Swegon's Paragon ventilates and keeps a perfect temperature whilst being quiet, draft-free, and highly efficient. The system does not use noisy fans to circulate the air in the room, but a centrally placed air handling unit that builds up air pressure. Nozzles in Paragon use the induction principle to mix fresh air with room air, distributing it along the ceiling, allowing for good circulation without draft. Cooling and heating is done with great accuracy via a waterborne heat exchanger. The system is easy to maintain, as no filters need replacing and no drainage is required. This saves running costs as well as investment. The standard version of Paragon sees the heat exchanger fitted with double water circuits, one for cold water, one for warm water. Each circuit has its own valve that opens and closes. This type of heat exchanger has limited cooling and warming capacity, as only one circuit can be used at a time. To enhance the system further, the innovative compact changeover valve, CCO, was invented by Swegon. The CCO valve allows for the use of a single circuit heat exchanger for both heating and cooling, meaning the entire area of the heat exchanger is utilised. This increases the heating and cooling capacity of Paragon by 60% and 20% respectively. This increased capacity can be used in many ways. One option is to adjust water temperatures, meaning chillers and heat pumps can run at more favourable operating modes. For instance, reducing the supply water temperature of a heat pump from 45 to 35 degrees typically increases the heat pump COP from 3.7 to 5.0, saving about 25% of the electrical energy. Thanks to these energy savings, Paragon also saves money and the environment. Regardless of what version suits your project the best, Paragon guarantees perfect comfort and the best energy performance. Our system makes sure the hotel guests return again and again.
The increased working range and the boosted cooling capacity is down to a number of key innovations. The basic principle of the comfort modules is that supply air builds up positive pressure inside the product's plenum chamber, and from there, it flows out at high speed in small jet streams. This generates a negative pressure inside the unit that draws in room air, a phenomenon known as induction. The room air passes through a heat exchanger where it's either cooled or heated as required. The mixed air is distributed across the ceiling thanks to aerodynamic outlets, and with the help of the Coanda effect, the airflow follows the ceiling. This ensures that the room is supplied with fresh air kept at the correct temperature, with no drafts and very low sound level. Thanks to Parasol Zenith's double outlets and double heat exchangers, a boosted airflow range and cooling capacity is achieved. In addition, the cooling capacity increases more evenly in step with the airflow. The new generation Parasol Zenith is a fully adjustable airflow from 0 to 100%, providing easy commissioning in CAV systems and great performance in demand-controlled ventilation systems. Because regulation is done directly in the product, it also reduces the need for external dampers.
Just a question that came up there on the chat about can these chillers be modelled in DEAP? As far as I know, not. Is that right? Technically, yes. The cooling side isn't modelled because DEAP doesn't look at cooling, but on the heating side, yes. So you just take the heating performance on the heat pump and enter it in DEAP. Even though it's providing cooling, the actual DEAP software doesn't look at cooling at all. It's just heating and hot water. it's a pity, because you're getting benefit here of free heating and free cooling for half the year, because if you have, say, for example, 90 or 100 or 200 apartments, and you have 50% of them on the south-facing aspect and 50% on the north-facing aspect, you could have a situation in mid-spring and mid-autumn where the south-facing apartments are overheating due to solar gain, and you have the north side needs a bit of cooling, so a bit of heating. Sorry, when the south side apartments are doing cooling, you're getting free heating going to the north side, and when you have heating demand on the north side, you're getting free cooling going to the south side. So therefore, you have an average efficiency of possibly 700% or more when you're doing continuous base heating and cooling simultaneously. Your summer cooling efficiency could be as high as 400%. Your heating could be as high as 380-400%. Your combined heating cooling could be as up and onwards of 700% to 800%. But that's not reflected in the app. So it's a pity. But look, I think that's another step forward for SEI, which is going to be difficult to implement. But yeah, we've been asked a lot lately from large developers that where can we implement cooling into our apartment, because we're getting lots of overheating. One guy rang me yesterday from a corridor in a very large building where he was saying it was 29 degrees Celsius in the corridor, because the centralized district system was running at 75 odd degrees Celsius, and the apartments were just melting, and they couldn't get any cooling into the place. So yeah, cooling might be a big problem long term, especially when we're getting our fabric U values and windows at triple glazing and 0.14, 0.15 in the wall these days. Any bit of solar gain at all, and we're getting very high temperatures in the apartments. The next video here is just one on the 4-pipe heat pump, showing you the heating cooling efficiencies that we're getting. Just asked there by Liam. It'll go through it here in a second. As you can see there by that, a lot of architects are putting in very, very large windows now in apartments, and that's just a no-go for cooling. So at this point here now, we're at mid-season, where I was saying, this time of the year and towards the October, November, where you have a bit of heating, cooling demand simultaneously, is where the efficiency starts to really show up. can see there that one single unit heat pump can be delivered with an output of up to 860 kilowatts of heating and cooling. So that's a pretty large number of apartments, all from one heat pump. Okay, just a question in there from Stephen as well. Said, I take it hot water demand is supplied by a separate heat pump system. Can you talk about the required certification required from SAI on these systems where EN 16147 does not apply? That's a bit of a bone of contention at the moment, Stephen, because you will not get EN 16147 for any commercial heat pump over 60, 70, 80 kilowatts. You won't get it because what are you going to test it to? What cylinder are you going to get to test it with? You know, if you have an 800 kilowatt heat pump, you know, you can't really pick a cylinder and test it with it because it's not possible. And you have such a large range of products from, you know, 40 kilowatts to maybe 2 megawatts on some heat pump products. And to get them all tested would cost an absolute arm and a leg. So it ain't going to happen. And that's something I need to get back to SAI and to talk about how this is going to be implemented properly. Especially if you don't have that 16147 testing, and I'm going to go through it here shortly on the workbook. There's a section here for hot water heating, and it's looking for the residential, you know, efficiencies on heat pumps when you're looking at hot water heating, which you don't have with commercial heat pumps. What I've been discussing with a lot of consultants lately is that what they've been using is, let's say your heating system is running at, say, 48, 50 degrees Celsius, say 50 degrees Celsius with your heat pump. They're using that then to tee off to go to a cylinder, a heat pump cylinder. So you're heating water to maybe 45 degrees Celsius, which is adequate enough for showers. Then using the same efficiency on heating as your hot water, and maybe using immersion heater as a top up and calculating the percentage difference between the heat pump doing it and the immersion heater doing it. There's a sort of heat pump. This is a sort of heat pump consulting group for non-domestic going on now. There are 2 meetings, I think, so far, but I was not able to go onto them. If anyone is interested, I can forward on details to the chair. Please do, Liam, yeah, because this is becoming a bone of contention at the moment, and it's very difficult to get you know, any answer from SAI about how we're going to implement these going forward long term, because I don't know of any manufacturer of heat pumps that has 16147 on a larger commercial heat pump. Like I said, what we've been doing lately is that we've been using the heating efficiency, because it's the same efficiency going to the cylinder as going to your wet system, your RADs or your HIU or your in this case chill beams, and then using electric heater top up or something and calculating the difference, say using a 400% at 75% and 100% at 25% and getting the average. There's a section inside the D app for calculating multiple inputs and taking the percentage across each one. Okay, we'll just keep going here with this. The next video here is just a little bit about the AHU and how it
The Gold RX air handling unit with a rotary heat exchanger has a unique way of securing the indoor air quality. The rotary heat exchanger is excellent at transferring energy from one airstream to another. But there is a risk of extract air leaking over into the clean supply air. To avoid this, Gold is equipped with a purging sector. But if the airflow is reduced, the purging sector may be insufficient. To solve this, Gold matches the rotor speed to the airflow, slowing down the rotor if necessary. Thanks to this unique solution, Gold delivers great supply air quality, even for demand-controlled ventilation. Air handling units with rotary heat exchangers recuperate energy by...
Just as a caveat in this, we spoke to the SAI on this going back last October, about how to implement this AHU into the DApp software, because it's a residential building. So you're looking at traditional MVHR systems, which are small, and you have feature data, or you have SAP appendix Q data for those AHUs, or for those air handlers inside in residential schemes. But this is a commercial AHU, and how to implement that into the app. And the first answer they came back with was, use your default figures, which is 2 watts per litre per second for the fan power, and around 70% or something like that for the efficiency on the AHU. Doing that, you're straight away non-compliant, because there's a minimum for heat recovery systems, minimum fan powers and minimum efficiencies, so the default knocks you out. So it took about 4 or 5 months of emailing and back and forth and questions and so on, and they came up with the solution that if you have the Eurovent data from the manufacturer of the AHU, they're allowing us to use the fan power that is calculated in that, and the system efficiency in that can be implemented into the app drop-down box for total MVHR with heat recovery. Put in your fan power, let's say it's 1.2, and your efficiency, let's say it's 75% or 80%, and that then got us across the line from a compliance point of view. So yeah, the thermal wheel here gives you very, very high efficiency, of course, and I think it's 1.22 or less. It has to be for MVHR. With traditional heat exchangers, we weren't getting that. So using thermal wheel, we get, especially with the central AHU, we do get that fan power right down.
Transferring it from one airstream to the other. In conventionally designed rotary heat exchangers, only a limited part of the airflow comes into contact with the air channel walls to release its energy. However, in the uniquely designed air channels in Swegon's Gold, the rotor makes the airstream turbulent, leading to increased contact with the channel walls. More energy is thereby released from the airstream, increasing the efficiency of energy recuperation. Thanks to the increased efficiency, each air channel can be made slightly larger, which reduces the pressure drop and saves fan energy. Compared to the conventional rotor, the Gold rotor has higher efficiency with less pressure drop, allowing for increased recuperation and lowering of fan energy consumption. Doubled profit for you, doubled profit for the environment.
Just going back there, this was a major factor with getting the system through the SAI compliance, where this fan power, getting it right down to where it needs to be for MVHR, was difficult, and using a high efficiency thermal wheels was the only way we got around it. Using default figures is not going to work.
The journey towards a quiet air handling unit always begins with a well-designed fan wheel. That's why we at Swegon have developed our very own, optimized to suit our Gold units perfectly. We have also taken care to design the entire fan assembly, balancing it as a complete unit. The design is compact and allows for easy maintenance. To cancel out any remaining vibrations, the fan assembly is attached to the unit using vibration absorbers and flexible connections. Our know-how and comprehensive approach to sound and vibrations guarantees that Gold is remarkably quiet, making it easy to use even in sound-sensitive environments. With the IQ Navigator control pad, Swegon's Gold has revolutionized the way we access ventilation systems. The dashboard gives you the current status of the system in one quick glance. If more real-time or historic performance data is needed, it's just one tap away in the log view. Any alarms that occur are easy to access and take care of. Guides are ready to assist you with startup and filter calibration. The many functions of Gold are accessible with just a few taps on the screen. And if preferred, The interface is accessible via Wi-Fi connection. Overall, the prize-winning IQ Navigator is full of great functionalities and makes Gold easy to access and explore.
Okay, that's just I suppose your 3 or 4 main videos on the gel beam, how they work. The air induction causes the negative pressure, which draws recirculation around and gives you that nice, comfortable indoor temperature and air quality. A bit on the AHU itself. If you haven't seen one before, it's understand it's like a very, very large domestic MVHR system, just a little bit more advanced on the controls. And then your 4-pipe heat pump. I know it's a 4-pipe heat pump with heating and cooling, but again, as we were asked, Liam said this is not allowed in DAP. The cooling side isn't, but the heating side is. And DAP only looks at heating and hot water, so we can implement that as long as you have the FEASH data for your different temperatures. You can input that into the DAP workbook. The question came up here from Moss was, how is a tenant charged for heating, cooling, and hot water? Again, you'd have to put in heat meters on your cooling circuit and your heating circuit. One particular client has asked us to come up with a solution for heating, cooling, ventilation for a large development. It's about 500 apartments, but it's over 2 floors of commercial. So there's about 14 or 15 retail units in the ground floor and first floor, from coffee shops to sports shops to restaurants, every kind of combination you can think of. And they require both heating and cooling as well, of course. So when the commercial is getting cooling, because you have a lot more cooling with commercial than you have with residential, the byproduct from the 4-pipe heat pump is free heating. So if you're a PRS scheme, you're holding on to these apartments, you're renting them out to the tenant, then Mrs. Murphy inside number 14 apartment, who's using her heat pump or her heating system is on, but she's getting free cooling because the commercial units are using a lot of cooling, then there's a large profit there for the developer, I suppose, or the PRS scheme owner, to charge out the heating at whatever rate, 8, 9, 10 cents a kilowatt, because it's coming for free from the cooling side. And vice versa, when you 500 apartments in the middle of spring and autumn and winter needing a lot of cooling or a lot of heating, the tenants in the commercial side are getting a lot of free cooling. So there's a large potential to make profit here on the billing out of the heating cooling system when you're looking at combined 4-pipe heat pumps. Just to go through the last one here, the Swagon products are called WISE. It's the WISE system, and they use their own WISE network. So it's a wireless radio frequency network that, first of all, scans the frequency around it to see where there's gaps in the frequency of the wireless systems, because you have lots of wireless networks now, from laptops, phones, everybody's on a different wireless network in their own apartment. So it looks at gaps in that wireless network and slots in there so it won't interfere with other wireless products in the building. And if you have a node, like you have room 1 here has three nodes, that could be the damper, that could be the 4-pipe changeover valve, that could be the room sensor. If one of those goes down, then it looks at the nearest node and creates its own self-healing network. So it's like a Zigbee wave, like its own self-creating mesh network. So it doesn't have to go from here right over to the furthest away one, back to the director to talk to the BMS. It goes from dot to dot to dot to dot around and works its way back through each node, back to the main central BMS system. So it creates its own mesh network, but it looks at the existing Wi-Fi network you see here in yellow or orange, and it slots in here in the green empty spaces, so it does not interfere with other networks in the building. So that means it reduces the install work because you've no cabling here, it's all wireless. From a commissioning point of view, with the Swagon solution, so like I said, each apartment could be pre-configured. So apartment 10 might have 3 bedrooms, 3 Paragon units, 1 in each bedroom, and 1 in the kitchen, dining, living room area. You're going to have 3 different airflows for each bedroom and 1 different airflow for your main living space. And you're going to have temperature requirements in the bedrooms and temperature requirements in the living space. You can have each component pre-configured, the damper and the 4-way valve and the sensor and so on, in the factory You walk around your handheld device, you scan the room, it says you picked up 7 devices. Is this correct? And you check yes, 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 so on. And then they're automatically pre-configured. Can also be changed on site too, but they can be pre-configured before they're delivered to site. So installation and commissioning is quite simple. Just a scanner, scan the product, and it comes up on the screen, and it's pre-configured. Okay, so like I said, you can actually upload your plans to the system, and you can actually locate the sensors and bits and pieces on the BMS system. You can make adjustments easy because it's wireless. It includes AHU data, heat pump data, room sensors, air quality, everything on the same BMS system, because it's all made by one manufacturer. Okay, so the advantage of this type of a system, this is the last slide here now, is you have very good indoor air comfort from an air quality point of view, VOC, from air temperature sensor, CO2, and humidity. So the one room sensor can give you all 4 options, and the ventilation system will automatically adjust itself with the temperature in the chill beam, and the air quality and the air volume will adjust itself to maintain an exact indoor temperature and to monitor the indoor quality of the air. This is also used in hotels, as you saw by the video. So you could literally have your key card linked to the system. So when you tap on the door handle on your hotel room, the ventilation system will start to ramp up, and it'll measure the air quality and adjust automatically. You leave the room, the door is locked, the system can ramp right down to background ventilation. So if you had a hotel application, this is the exact same solution. You can have it linked to your key card. So there's no filter in this because it's not a wet coil like you'd have with a fan coil. So there is very little maintenance involved here. There's no noise in this chill beam because there's no fan. The fan is 100 yards away inside in the AHU. There's no condensate because there's no wet coil. The AHU, or sorry, the chiller temperature is up to 1421. Therefore, it's above dew point all the time, and it can be preconditioned at the AHU as well to remove humidity. Therefore, you've no condensation trays or drains to be worried about. And that's again another maintenance issue. The water temperature is not too high. So the other big thing here, and I had about four phone calls today from various consultants and even developers, builders, doing pretty big high-rise over 18 meters. If you're over 18 meters now, you have to fire penetrate and fireproof each penetration, and that can be expensive. This particular job we're looking at for one developer, the architect is looking for 0 wall penetrations if possible. It's a very high-end facade. It's a very, I suppose, sexy-looking facade that you want to have minimal penetrations as possible. With this solution, you've none, because your supply air is coming through the chill beam, your extract air is coming back through the bathrooms and kitchen back to the AHU. So on the actual apartment or on the bedroom itself, you have no wall penetrations. So the architect here was very happy with the solution because it meant nothing goes through the wall, and that can be a factor. It can be a cost. It could be up to 400, 500 euros per penetration, depending on the type of facade you have. Heating and cooling per individual room, no rads or piping for same, no need for HIUs. So it's a very neat solution from one supplier that is hopefully going to start gaining ground. Hot water was a question asked a while ago. So hot water can be done in several ways with the system. You can simply use electric hot water heater. 2 immersions plugged into the cylinder, away you go. It will affect your DAP, of course, as long as your heating efficiency is high enough, and your AHU efficiency is high enough with your heat recovery, you might get through without having any other renewable technologies needed. You can get a heat pump water heater, of course, but that means you're back to 2 penetrations, air in and air out with your hot water heat pump. You can use central storage. Again, it's done quite popular in Scandinavia, where you'd have every apartment in Scandinavia, as I've seen over there. I've been over there several times. You'd see 4,000, 5,000, 6,000 liters of water stored in the plant room, and that's sent off through a distribution system. Again, that could have a cost implication. It depends on the type of building and the length it runs. You could also use a heat pump cylinder, like a standard Kingspan Joule type heat pump cylinder, where you preheat the water using the same water coming from district heating system, same temperature. Let's say it's 48, 50 degrees. If you put in 50 degrees through a cylinder, you'll get typically about 43, 44 degrees stored hot water, which is enough for your showers and so on and washing hands. You can have a boost button in for boosting up to 60 degrees for your Legionnaires, and for nighttime boosting for high temperature hot water in the morning for your peak demand. The cost, if you had to run that cylinder just on pure immersion heater alone for the whole year, let's say your day rate is 15 cent, night rate 7 cent. Your typical demand for hot water for an apartment for the year is about 2,000 kilowatt hours. So you say, let's say you had 2/3 night and 1/3 day for nighttime boost. Your total running cost would be about €190, which is not the end of the world. If you had, we'll say 60% of that preheated by the heat pump, you could bring that cost down to maybe €90 or €100, maybe €120 for the year for hot water heating. And again, each of those four methodologies would have a different input in the app. The last one is where we're looking to get guidance and clarification from SAI, because we don't have an EN 16147 test. It's the same temperature as a district heating system. So do we use the same SPF on the heat pump for space heating for hot water heating? I can't see why not. And then use a percentage of that for immersion heater top up at nighttime. There is a section in the app that allows you to put in multiple heat sources for doing hot water and multiple heat sources for doing heating as a percentage, and it calculates your overall BR from those multiple inputs. Okay, so that's that part. Just going to have a quick look here at the workbook. So I'm going to share this screen here. Okay, this is the heat pump workbook for, I suppose, commercial heat pumps that the SEI have brought out. Really, you have two main tabs. Really, you have obviously your project details here. You have your DAP entries. So the first 4 or 5, 6 lines here, you bring straight from DAP. So the first one here is your total heat loss from DAP. You get that from the tab. You go to your results tab, you'll see it there as the sum of the losses from the fabric and the ventilation windows. It's the total heat loss taken from the app. In this particular apartment, it was 88.43 watts per meter Kelvin. Next line down is your annual space requirement, your total. Again, you take that from your, go to your DAP4, you go to view assessment, and you go to your gains and losses. And you take that from your DAP4 file in there. Obviously the area of the dwelling, which is fair enough. The living area, that's fair enough. If you have a secondary heat source, put it in there. In this case, we don't. Let's say you had, I don't know, for example, a stove, which you wouldn't have in an apartment, but you might have in a house. You put that in there. Fraction of heat from CHP. In this case, we have 0. Output from main water heating. I left it blank on purpose because I'm just looking at the heating here, not the hot water, because we don't have that EN 1614 test data with the commercial heat pump. And again, like I said, I'm trying to get clarification on this from SAI, how we go forward with this. But that will go here. As, again, you take that from your view assessment, your water heating tab, and you'll see the total demand for hot water. It could be, say, 2,000 odd kilowatt hours a year. Group heating charged, yes, your energy factor for electricity is 2.08. The hot water storage, again, let's say you had a 150 litre Joule or a Kingspan Albion tank, that would go in there. Okay, so then you have 3 heat pumps. In this case, we have 1 heat pump. You could have none. Heat pump, which is ground source heat pump, water source heat pump, air to water heat pump, doesn't really matter. It's called a heat pump. The option there is also for exhaust or heat pump. You could have a case where you're ventilating the building and using one very large heat pump to recover the heat from the ventilation system. That would go in here as well. So in our case, it's an air to water heat pump. Type of heat pump for water heating. In this case, I've none because, as I said before, we're looking for clarification on this. Percentage of heat produced by the heat pump for the space heating, in this case, it's 100%. Is the heat pump in a group heating scheme? Yes or no? Is the heat pump preconditioned by some other source? Yes or no? In this case, it's not. It could be preconditioned from a waste recovery system, or could be preconditioned from a gas system or whatever, but in this case, it's not. Next tab is your heat pump tab. This looks very, very similar to what you'd have in your old-fashioned DEP workbook for your residential heat pump. So again, the blue ones are pre-populated. What's interesting here is, and I don't know why they do this, is that you put in your group heating system total flow area served by the heat pump. In this case, it was about 7,000 square meters. Manufacturer, make and model, type of heat pump, air to water, variable output, same as before. Heating test standard 14825, same as before. Nothing changes there. Your TOL and WTOL, again, nothing changes there from previously. Razors, fan coils. It's called a fan coil because it's a chill beam, so there's no drop down for chill beam. It's in essence a fan coil. Underflow heating, no. Design flow temperature 45 degrees, 35 degrees, 55 degrees, whatever the case may be. Operation hours 16, 18, 24, doesn't really matter, whatever the operation hours is. Lack of space heater, no, there's not. Then down here, it's the very, very same as you have for your domestic heat pump. Your high temp data, low temp data, medium temp data, and very high temp data. In this case, we have our low temp and high temp. So at 35 degree, again, you go to your product fiche as you would have with a traditional Hitachi Mitsubishi heat pump you'd see in domestic. You get your -7, 2, +7, 12 in your TOL. Put that data in here for capacity and COP. The same with the high temp, your 55 degree data and your 35 degree data. And lo and behold, it spits out a space heating efficiency, say 342%, whatever the case may be. If that was running for higher, say 24 hours a day, which most likely would be 24 hours, that would probably increase to 400%, I would say. Yeah, 407. That thing goes back into your first page. It automatically populates it. There you go, your 407%. And that is the figure then you use in your heat pump workbook to give you your final BER. Again, for hot water heating here, we have nothing because I didn't pick a hot water heat pump because we don't have one for commercial, unless you have multiple smaller ones that you can use for hot water heating, but then you wouldn't do that in this case. We're trying to get, like I said, we're trying to get clarification from SCI on how this is implemented properly using the single heat pump for both heating and hot water if you don't have EN 16147. And like I said, in my eyes, it's quite simple. Your space heating heat pump is also providing hot water at the same temperature. So you'd use that to precondition the cylinder and you top it up with electric heater. And you fraction out that percentage. Let's say it's 65% heat pump and 35% immersion heater. And you put that into your DEP workbook then as 65% at 400% and 35% at 100%. And that will then give you your overall efficiency for your hot water. That's how I think it will pan out. So apart from that, I think that's about it. The hour is just up. So if any questions, happy to answer. Or Stephen, you have any questions or any input there yourself?
Mike, I have a question there. This is Moss here. Can you hear me?
Yeah, can Moss, yeah.
I was just wondering there, at what point in time was the sweet spot? How many apartment units are you talking when this starts to make sense from a
good question. That's the $1 million question. I did some investigation on this in the last 4 months, and it looks like it's up around the maybe 170 odd, 160, 170 odd apartments, depending on the density of the apartments, depending on the shape of the building. If you have a very, very simple block, old-fashioned block, it's quite simple. If you have a H-type shape building or a complicated building, it can get more expensive. So it's horses for courses, but there is a sweet spot, and it'll vary from block to block. But I'd say about 140, 50, 60 apartments upwards, it'll make financial sense to go to district heating. Unless it's a PRS system and you have some retail in the ground floor, then it makes complete sense.
Okay.
Because you're getting free heating and free cooling, and depending on time of the year.
Gotcha. Thanks.
From a cost point of view, we invited a handful of fairly big mechanical contractors, the big boys in the industry, to come in to look at pricing up a system based on a made-up apartment block that we kind of gave up, 90 or 100 apartments on a made up a block of, just to give an idea of price comparisons. And a typical centralized system with a heat pump using RADs and HIUs and hot water cylinders and bits and pieces came in around 17,500. without cooling, which included your pipe and fittings and labour, your soil, sewers and waste, your fitting the bathroom suites, fitting the showers, doing the whole mechanical package, came around 17.5. When you incorporate this solution, you're bringing in cooling as well. It works out around 19.5. So about $2,000 more, but you have way less cabling and wiring because it's mostly wireless, and you have no penetrations on the wall, which could be $1,000 or more depending on the type of facade. So there's not a lot in it, but what you do get is you get the cooling, which is a very big bonus on the system. And also, if you have commercial attached to the building, it's a no-brainer because the same system can do both the commercial and residential, and you get the byproduct of free heating and free cooling, depending on who's doing what. So the profit margins can be quite big.
Okay, thanks for that, Mike. I see one question just popped in there from Christopher. Has Swagon agreed a methodology with NSAI for ventilation testing for this system? So
I suppose it come under the answer I don't know, but it come under I presume the same ventilation validation as you would have with a domestic system, supply air, return air, air volumes,
and the SAP system would be registered on the SAP system there as well, I presume.
On the SAP, no.
Mike, would that be a DCV system? What would it be?
It's pretty much a DCV, yeah. It's continuous ventilation, but it's demand control as well. So it's looking at the air quality and looking at the ventilation requirement per room. So if you have an unoccupied room, the air quality, or the air volume will drop right down to background. Something like it have with DCV. They actually call it WISE DCV system. So it is demand control ventilation, yeah. But it's also heat recovery. It's a bit of both kind of mixed together.
I just wondering if they talk to NSAI about a methodology for it. It's a bit of a hybrid system.
Yeah, it's demand control ventilation, and also with heat recovery, because you're extracting from wet rooms as well, going back to your AHU, and you're recovering the energy there through a thermal wheel, bring it back down then as a supplier into your living spaces. So it's in essence a very, very large mechanical ventilation heat recovery, just a bit more refined, because it has air quality and humidity sensors per room,
And that's how it is entered in, I suppose, in DEEP is the most important.
It's entered in DEEP as a full MVHR, yeah.
Right, okay.
And we had that in writing from SCI. It took us months to get it, and they finally came back and said, put in as full MVHR, put in your fan power as per the Eurovent certificate, put in your thermal wheel efficiency as per Eurovent certificate from the manufacturer. And they gave us the kind of green light on that,
It might be no harm, Mike, to check that with NSAI as well. To take their read on it, because no point in just getting the SCAI approval if it's there's going to be roadblocks on the ventilation testing and validation side of it.
Yeah, well, I can't see it being a roadblock because it will be a very highly efficient, accurate system because it's monitored and it's balanced properly on commissioning, like any system has to be. So yeah, but it's a valid point to run it by the NSAI.
Thanks, Christopher. And just, I suppose, we were jumping between commercial and domestic here a bit, but I presume in NEEP, this is entered as a passive chill beam displacement system.
Active chill beam. Active.
So it's active. I thought it might be passive, as there was no fan in the system. So
no, it's an active beam because your AHU is your active side of it.
Okay, so passive would be literally there would be no fan in the system.
Correct. Yeah, it's using natural air currents and induction. You don't get nowhere near the amount of heating and cooling from a passive beam as you would an active beam.
Okay, and then therefore we've all our efficiencies that go into NEEP from the seasonal efficiency of the thermal wheel. We have all that data available, and then it's entered quite simply. Heating, cooling, EERs, the heat pump, all that information is supplied. So that's fairly straightforward to enter it into NEEP. Then and then
it's just our biggest problem with Steam was trying to convert this commercial solution into residential application, putting a square peg in a round hole when it came to DEP, as always. And DEP seemed to be no blocking design from a compliance point of view, where you have innovative, really good technical solutions, but because DEP says no, it's not getting designed, which is a bit of a crazy situation to be in,
Yeah, they're struggling to keep up with the innovation that's out there, right?
Absolutely. This is nothing new. This is going on with a long, long time. Chill beams and AHUs and heat pumps are around with 20 odd years. Like I see my first chill beam over in Sweden about 18 years ago, wondering what it was,
Yeah. So I know from speaking to Scandinavian suppliers as well, they're a bit scratching their head with which especially the N16147 was one that came up. And I say Liam there was asking if there was a precedent for SCI accepting a model of apartment in Neep. Well, I suppose unless it was classed as a hotel or a student accommodation,
it hasn't been yet,
it wouldn't be modelled in there anyway,
no.
so it wouldn't be classified that. Okay, so I don't think we have any more questions, and we've gone a bit over the hour, so I think we'll wrap it up there. And thanks.
Yeah, I think it's an interesting one to keep an eye on, because there's a lot of people looking for cooling out brought into residential applications, and this is a nifty way of doing it. And we've a couple of guys now on the verge of pushing the button, you know.
Yeah, certainly is something that's coming upon my desk quite a lot anyway. Okay, Mike, listen, thank you so much for delivering both webinars, both last night and this week. Thanks to everybody for coming, and thanks to everybody on the committee, and in particular on the Stream 1 side. And a huge thanks to Eleanor there, who is behind the scenes making everything happen. So thank you very much for that. And we'll hopefully be back in September with a new series of webinars. So thanks everybody, and good evening. Have a good summer.
Okay, take care.